This is Dr. Holt. This video is on the solutions to test 4 balanced forces. Question number 1, you have 2 forces of equal magnitude in opposite direction acting on a system. Over here I've drawn a free body diagram. Now there's several scenarios that can happen here. If your forces are balanced, the object can be at rest, it can be just sitting there. However, the object can also be moving upward at a constant velocity, side at a constant velocity, or at any angle at a constant velocity. Because as long as the forces are balanced, all that occurs will be no acceleration, but velocity can be constant or velocity can be 0. So in this case, your answer is going to be B. All statements are possible. Number 1, the system is moving to the right with a constant velocity, the system is moving up with a constant velocity, and the system is at rest. Question number 2, the answer to this one is going to be A, and I'll show you how to get that. This is a unit conversion problem. We want to find the mass in kilograms. So we start out with 130 pounds. We are given that 1 pound is equal to 4.45 newtons. So since we have pounds in the numerator, we immediately put 1 pound down here in the denominator. We put 4.45 newtons here. Now when we do our multiplication here, our pounds will cancel out and we'll be left with just newtons. But again, we want to get our mass. Now we know that force is going to equal to mass times acceleration. And in this case, when we're doing weight, then we can basically say weight, which is a force, is going to be mass times 9.8 meters per second squared. So all we have to do on this one then is to put 4.4. Oops, let me come back on that. Let me fix that. Let's do the multiplication first. Let's take 130 times 4.45. So I take 130 times 4.45. That's going to give me 578.5 newtons. 0.5 newtons is equal to mass times 9.8 meters per second squared. So all we have to do here is mass is going to equal to 578.5 newtons divided by our 9.8 meters per second squared. And when I do that, it gives me exactly a value of approximately 59.03 kilograms. Alright, so that's the answer to problem number 2. The problem number 3, a ham pushes vertically down on a 1.5 kilogram book with a force of 10 newtons. Again, the easiest way to solve this is to go ahead and draw your free body diagram over here. We have our vector coming down. This can be our force of gravity, and our force of gravity here is going to equal to the mass 1.5 kilograms times 9.8 meters per second squared. When I do that calculation, 1.5 times 9.8, that's going to give me 14.7 newtons coming down. Okay, we also have another force of 10 newtons pushing down, so we draw it coming down too. And that's a pushing force. I'll draw my vectors here. That's equal to 10 newtons here. And then I'm going to have my normal force going back up like this. And obviously, if we sum our forces in the y, which I will do, summation of forces in the y is equal to 0 because this book is not going to be accelerating, back through the surface. So that's going to give me my normal force minus 10 minus 14.7 is equal to 0. Move these to the other side. My normal force will equal to 24.7 newtons. Now the question asked you here from the force diagram, which of the following statements is going to be true? Well, we know right now, let's look down through here, the pushing force is greater than the normal force. Well, we know right now that's not true because my pushing force is 10, I got 24.7. Let's circle that. So we know this one is incorrect. Pushing force is equal to, no, we know that's not correct. Pushing force is less than, yes, that is correct. Normal force is 0, we know that's correct, not correct. And again, impossible, we know that's not correct. So our answer is going to be C. Okay, what is the magnitude of the force the table exerts on the book? Well, we just worked that right there. That's going to be our 24.7 newtons. That's going to be our normal force, so we know that answer is there. And the next question, what is the net force acting on the book? Well, remember, we summed the force right there. There's your net force. Your net force is going to equal to 0 because these forces balance everything out. And we know if the net forces are not 0, the book would have to accelerate, and the book does not accelerate back through the surface. It cannot accelerate left and right because the person is only pushing down. So this answer has got to be A, 0 newtons. Okay, next question here, question number 6. Imagine two scenarios. The first scenario, a baseball on the surface of the moon. In the second scenario, the baseball is on the surface of the earth. What is the same in the two scenarios? Well, again, if you drew yourself a free body diagram on Earth, we'll do that one first. In this case, it really doesn't matter what the mass is. We would have the mass of the baseball times the gravity of Earth. And this would be my normal force pushing it up. And again, these values would have the same magnitude. Now, if I drew that on Earth, on the moon, we know that the gravity on the moon is going to be less because it has less mass. So we'll draw this guy coming down like this. Let me slide this over just a little bit. And then we'll draw our normal coming back up like this. This would be my F normal. Again, this is mass of the baseball times the gravitation value of the moon. Now the question is, what is the same? Well, we know the mass is not going to change. So the strength of gravity in the two scenarios is the same. We know that's incorrect because the strength of gravity on the moon is going to be less than the strength of gravity on Earth. The mass of the baseball in the two scenarios is the same. Yes, we definitely know that's true. The weight of the baseball is the same. Well, this is equal to your weight. If the baseball was sitting on the scales, the normal force would be the scale pushing back up. We know right now that this value here is going to be less. So this is incorrect too. So the answer can only be B. All right, the elevator problem. Again, key information on this one is to see if you have constant velocity. And if you read this very carefully, elevator is being lifted up, elevator shaft at constant speed, so we have constant velocity. If we draw our free body diagram again of the elevator, we'd have this going down and this going up. And I'll just label these. This would be the steel cable, the tension in the steel cable, like this. This would be the mass of the cart or car here times gravity. Now the question says the force of gravity acting on the elevator is less. Well, we know right now if we sum the forces in the y direction, we must get 0. And the reason we get 0 because they're constant speed, and we know the acceleration is equal to 0. So we know, again, this is going to be incorrect. The force of gravity acting on the elevator is equal to the force exerted by the steel cable. Absolutely true, because we know this one and this one are going to have the same magnitude. And we could go back through these and quickly do the force of gravity acting on the elevator is more incorrect. The only force acting on the elevator is that of gravity. Elevator, no, that's not true because we have the rope pulling back up. And this is incorrect too, so it has to be B. Alright, question number 8. Again, always draw the free body diagrams of these. We have a 10-gram ball, ping pong ball. So we'll draw that coming back down here. This will be the force of gravity. Again, it's going to equal to the mass, and you need to change that to kilograms. So divide that by 1,000 to get my kilograms times 9.8 meters per second squared. That's going to be the force of gravity. You also have this string, so we'll have a tension coming down here. And we'll have a buoyant force that's going to balance these up. So we know right now our buoyant force is going to be pretty big. Here, okay, the question says, From your force diagram, which of the following statements about the magnitude of the forces acting on the ping pong ball is true? Well, let's look and see what we got here. Well, okay, we're talking about buoyance forces. We know right now that this guy is going to be the largest force because it's going to be the sum of these two. So we know this is incorrect. We look at this one here. Is this the tension here going to be greater than this? No, that's incorrect. Is the tension? Yes, that is correct. And we know that cannot equal to 0. And oops, I got that wrong. Incorrect and incorrect. So the answer has got to be C. Nope, go back to that. We need to do number 9. What's the approximate magnitude of the tension, the force acting on the ball? Well, we know the buoyant force is 1 Newton here. So can we not just sum forces in the y direction, set it equal to 0? Anything goes up positive, we'll get 1 minus the tension in the string minus 10 over 1,000 times 9.8 is equal to 0. We'll solve that. Move this the other side, we get 1 minus, and we'll run that right to the calculator real quick. Maybe we'll take 10 divided by 1,000 times 9.8. That's 0.098. Again, we move this to the other side. That's going to tell us what the tension is, and that's going to give us a value of approximately 0.902. And that's supposed to be newtons. So if we go up to our problems and we see our solutions, and the only thing we have that's getting close to that one is that one right there. Okay, problem number 10. You have a burglar pushes the 200 kilogram refrigerator up a 10-degree incline, constant speed. Okay, again, draw the free body diagram. Come over here. We have this coming this direction here. This would be the force of gravity. Again, that's going to just be the earth onto, what is that, the refrigerator. Alright, and again, we know that's going to be 200 kilograms times 9.8 meters per second squared. We'll have our normal force coming back up, and we have a pushing force here. Now we know right now if he's pushing this, there has got to either, let's make sure there's friction. Okay, there's no friction. So we know that the component of this is going down is going to be balanced with the pushing force. So we'll label these to be a pushing force. This would be our normal force. Alright. Now what I like to do is I like to tilt my axes. So I have one coming down this way and I have one coming this way. Again, this is being parallel to the surface. I will color those red, and then we'll make those thin so you can see them. Okay, I'm going to call this my X, and I'm going to call this my Y. And I'll say anything goes up will be positive, anything goes up this way will be positive. Alright, what I like to do now is I like to take the gravitational and break it into components that's going to be parallel and perpendicular to these surfaces, because this one is parallel to this one, and this one is parallel to this one. And while we're at it, we might as well just draw those while we're at it. We get a vector here. This is my pushing force here. This will be my normal force here. Okay, we'll take this one and break it into components. And again, what I've talked about in class, I like to do is, if it's going in this direction here, I draw the normal coming this way and the one parallel like this. This being my right angle right here. If this is 10 degrees, this will be 10 degrees here. Now we'll run this as our force of gravity. That's going to be our 200 times 9.8. So 200 times 9.8. Yeah, it gives me a value of 1,960 newtons. We'll Okay, to find this one, we will take 1960 times the cosine of 10. That'll give me a value of 1930.22 newtons. We'll go ahead and add that to our tilted free body diagram. So we come down to here. This will be the force of gravity in the y direction, and that will equal to 1930.22 newtons. This value here will be 1960 times the sine of 10. That'll give us a value of 340.223 newtons. We come over here, we add it to our tilted free body diagram, and this will be the force of gravity in the x, and that will equal to 340.223 newtons. Now the magnitudes here will be the same, and here will be the same. First question, it says determine which of these is going to be true. Now if you go back to the original free body diagram and think about it from a logical standpoint, you have the force of gravity coming down here, which we know is 1960 newtons, this direction here. Well, we know right now, looking at this one, we know that the pushing force must be at 340.223 because these have to be balanced because they got constant velocity. So we know right now that this is a true statement, that the force of gravity is larger than push. This says the force of gravity is equal to the normal. Well, the normal is going to be 1930, right? Because this and this have got to be the same magnitude because the object cannot accelerate through the surface. So we know this is incorrect, and we know this is incorrect, and we know this is incorrect, and this is incorrect. So it has got to be A. Now, since we already have these values, we can do the other ones very quickly. It says, what is the magnitude of the force the burglar exerts on the fridge as it pushes it at 2 meters? Now, this means nothing. This could be 2 meters a second. It could be a billion meters a second. As long as it's constant velocity, the forces have got to be balanced. So we go back here. That's 340.223. This has to be 340.223. So our value here has got to be this one here. What's the magnitude of the normal force? We go back to our free body diagram. This is 1930 coming down. The normal has to be 1930 pushing back up. So this one has to be this value right here. All right, let's keep moving on. The chandelier problem. Again, I draw the free body diagram, and I would recommend this. If this angle is 50, this angle here has to be 30 degrees because then you have a straight line. This has to be 180. So when I draw my free body diagram, I will have this will be the force of gravity of the chandelier coming down. I will have this value going back up, this, and I will have this value going back up like this. So this will be force in number 2, we'll call it tension 2. This would be force T1. Okay. Now if we look at this problem here, the answers only have to do with the relationship between T1 and T2. We know we have to be balanced across the horizontal. So the horizontal component of this one, break it into the components here. Draw that a little better. Get the right one here. These are the two components. We know right now that this one and this one have got to be the same magnitude because they have to be balanced out. So we know right now the tension here, the magnitude in this, in the cable 2 must be greater than T1. So if we go down through our answers and look at the answers on 13, the answer has got to be, let's see what we got here, the normal. Oh, that's T1, I'm sorry. T1 is less than T2, that's absolutely correct. And the rest of them doesn't, I mean, the rest of them cannot be true because, again, the magnitude of this vector here or this tension must be greater than this because the horizontal component of this must balance out this one. And same way with the gravitation, the vertical component of this one must equal this one to be balanced. Okay, then answer the 13. And then 14, you're given the mass is 75. All we have to do then on this one is go back and make this into 75 times 9.8 coming down. Now what we can do here is we can sum the forces in the x direction, set that equal to 0. We can sum the forces in the y direction and set that equal to 0. When I do my x's, I will get ft1, we'll make that minus because it goes to the left, plus ft2 cosine of 30 degrees is equal to 0. We have, now we'll sum the forces in the y direction. The only thing I have going up in the y direction is going to be t2. So ft2 times the sine of my angle here, which is 30 degrees, minus 75 times 9.8 is equal to 0. We will find ft2 first. To do that, I take 75 times 9.8. I will divide it by the sine of 30. That gives me a tension of 1470 newtons. I will take that value right there, I will put it back in right here for 2, and we can solve for ft1, so minus ft1 plus 1470 newtons times the cosine of 30 is equal to 0. So if I take that times the cosine of 30, I will get the magnitude of F tension 1 is equal to 1273 newtons. Let's go over to our picture, and number 14 has got to be C, which matches what I just calculated. Okay, on this picture here, again, pretty much everything here is going to be based upon you being able to draw a good free body diagram. Alright, so we know that the force here and this is going to be 100 Newton given the problem. So we come over here, we draw the free body diagram right here. We will have the force of gravity coming down. We will have this force going back up, and we must have some type of normal force going back up also of the surface pushing back up. This will be my F normal. This will be my 100 newtons. And this will be force of gravity, which is again equal to 20 kilograms times 9.8 meters per second squared. We'll go ahead and put the values into here. That's 196 newtons. Oh, yeah. So I'm just going to go ahead and run the values, and then we can look at the answers very quickly. Alright, if we sum, oh, we must have friction in there too. Let me do this too. This object has got to be balanced, because this is going to have an X component, so I have to have friction back this way here. Now let me read the problem real carefully if it's sliding. So moving at constant velocity, so the friction has got to be kinetic friction here. There's the free body diagram. Now we're ready to do it. Summation of forces in the X direction must equal 0. Summation of forces in the Y direction must equal 0. Well, to get the X's, all I have to do is to say that F of K will make it negative because it's going this direction here, plus 100, and the angle given is 30 times the cosine of 30 degrees must equal 0. We can find Fk immediately. We'll take 100 times the cosine of 30 degrees, and that's going to give me 86.6 newtons. Now to find the other ones, we can do summation of forces in the y direction. So that equals 0. When I do that, I'll get my normal force going up here, plus 100 newtons times the sine of 30 degrees minus 196 is equal to 0. We will solve for F normal. So I get 100 times the sine of 30 minus 196, and that means 1 normal must equal to 146 newtons going up like that. Alright, now let's go to our questions and quickly answer those. And again, I can answer everything just based upon my free body diagram. Is the force of gravity greater than the force normal? Well, I got 196. My normal is 146. The right answer is right there. I mean, you can go back through these, but you know this is incorrect, this is incorrect, this is incorrect, and this is incorrect. So it just happens to be A, had to be the first one I came to. But again, force of gravity is greater than Fn. Force of gravity is 196. My normal is 146. Now let's see if we get this one. What's the magnitude of the normal force? Well, I just ran that number, did I not? The normal force is going to be 146 newtons. And then what's the frictional value that I calculated? 86.6. So that value is 86.6. Alright. Well, I have, I think, 3 more problems to do, and we're all done with reviewing this test. This problem here is probably the hardest problem on the test, but again, draw yourself good free body diagrams. You got a 2 kilogram block slides down the ramp at a constant velocity, so we know we have balanced forces. The magnitude of the frictional force acting on the block is 10 newtons. So come here, I will draw 2 free body diagrams, one in the standard position and one tilted. This is the one just in standard. My frictional force is 10 newtons here. This is going to be my abnormal. This is going to be my force of gravity. Put vectors on there. Force of gravity is going to equal to 2 kilograms times 9.8 meters per second squared. That's going to give me what? 19.6 newtons coming down. Alright, well then I tilt everything like this and like this. I will again color code everything like I usually do. Make this red and make that thin and dotted. Okay. I'm going to let this be X. I'll let anything that comes down be positive this time. And this will be Y and positive. Don't get too excited about which way you do these. It's positive, negative. Just establish the system and stay with it. Okay, so I will go ahead and add the 2 that I know. Let me do a vector. I got 10 newtons coming here. I will have F normal coming up here. Now what you want to do is go ahead and get this thing in the components. Again, we talked about this in class, but I draw this like this, and if it's going down inclined in this direction, I draw the normal first like that, and this one like this. Again, this is the right angle here. We know right now that this value here is going to be 19.6 newtons here. I will make this into theta. We do not know what theta is. Now, if this is theta, these 2 thetas are going to be the same. So right now we know this value is 19.6 cosine theta, and we know this value is 19.6 sine theta. So I bring those in and bring those in here. I will label this as 19.6 sine theta, and I will label this as 19.6 cosine theta. Alright. So it really doesn't matter which one you do. I'm going to go ahead and do these. Can I not say that minus 10 newtons plus 19.6 times the sine of theta is equal to 0? I will solve for theta. Move the 10 over. So I get 19.6 newtons. Sine theta is equal to 10 newtons. Sine of theta is equal to 10 newtons over 19.6 newtons. Newtons cancel out here and here. So can we say that theta is equal to the inverse sine of 10 over 19.6? I will run that in my calculator. I will do second sine. Again, make sure your mode is set for degrees. Second of sine of 10 divided by 19.6 degrees. That gives me a value of 30.677 degrees. That means that this angle right here is also 30.677 degrees. Alright, now I just have a fairly simple problem because we know h over 12 is the tangent of theta. So can I not say that h over 12 is equal to the tangent of 30.677? Bring the 12 up. H is equal to 12. Tangent of 30.677 0.677. So I do that real quick. And that gives me a value of 7.11, or actually 7.12. So my answer here has got to be this value right here. All right. The last problem is here. This is 1920. A man's holding a wooden block at rest on a trough, 55-degree incline. All right. So again, as I always say, if you draw yourself a free body diagram, you cannot get these problems wrong. And again, it's just a methodical free body diagram. So I'm going to make this tension force is going to be 1,000 newtons. The weight coming down, that is a force. You do not multiply that by 9.8. I don't really know that one. And let's see here too. What are we looking for here? We've got some static friction. Okay, again, make an assumption about what direction you think it's going. The math will fix it for you. It doesn't really matter. So I'm going to say I think it's going up. Force of static friction here. All right, now I tilt my axes as I always do. You have to do that. You don't have to, but it's going to make your problem so much easier. Draw like this, and I draw my normal like this. Again, I try to make that look like a right angle. Change that to red. Change the thickness, and there's my values. I will let this value be the y value here, so be positive, and I'll let this be the x value, and that'll be positive here. All right, I go ahead and immediately bring in the 1,000 here. It's going to be parallel going up like that. I make that value 1,000 newtons here. I go ahead and draw my static friction this way because I think it goes this way. If I'm wrong, again, the math will fix it, which is wonderful. I make that my static friction here. Now I'm going to break this into components just like we always do. I come over here like this. I draw my normal force like that, and I draw this one down like that. There again is my right angle here. I'll do that in red like I usually. That's my right angle there. If this is 55 degrees, this angle here has got to be 55 degrees. This is my 1500. This is going to be 1500 cosine 55. This is going to be 1500 sine 55. I will run those values very quickly. 1500 times the cosine of 55 degrees gives me a value of equals to 860.36 newtons. 1500 times the sine of 55 degrees, that gives me a value of 1228.73 newtons here. All right, now I add those back to my free body diagram. I will get 1228.73 newtons here. I left off the other two. I don't know why I did that. Let me just put those back in here. I'm sorry, when I do this, I should have drawn my normal. I apologize. I don't know why I left that off there. It's really kind of dumb of me. This is my normal here. Again, the other one coming down is going to be this direction here. That value is going to be your 860. So right now we know normal and this have got to be the same because this object's not going to accelerate through the surface here. So now to find my static friction, all I have to do is sum forces in the x, set that equals 0, anything goes up positive, I get fx, draw a vector, plus 1,000 newtons minus 1228.73 newtons is equal to 0. Obviously you can look at this and fs has got to be equal to 228.73 newtons there. So we know right now this is the answer right here. Again, what direction did the force of static friction point? Well, the static friction has got to go up the incline. Again, I just guessed right, but if I would have worked this value and I had it going negative, then I would have had this negative and I would have got a negative here, meaning I had it go in the wrong direction. All right, That's the solution to the balanced force test. I hope this video was useful. I would watch it several times because this information will be coming up again when we do the final exam. All right, best of luck.